Hello, this is the lecture 2 of chapter 10, and now we will go through the variation of pressure with depth, because we have seen we know the pressure at this point. Say at the same horizontal position the pressure is same if the fluid is at rest, and if the at the same horizontal position the pressure is not same, that means there is a flow in the fluid. Now we will go through the variation of pressure with depth. Suppose we know that this is means the horizontal position 1, and 1 minute. Suppose this is horizontal position 1 and this is horizontal position 2. So if we know the horizontal position of this point, can we calculate the horizontal means the pressure of this point by knowing the pressure of point 1? In this section we will see what if we can find, how we can find, and what is the formula for that. Consider a fluid at rest in a container in a figure 10.3. Point 1 is at height h and above a point 2. The pressure at point 1 and 2 are P1 and P2. This is the diagram. This is P1 and this is P2. Consider a cylindrical element of a fluid having area of base A and height h. As the fluid is at rest, the resultant horizontal forces should be 0, and the resultant vertical forces should balance the weight of the element. The forces acting on the vertical direction are due to the fluid pressure at the top P1A acting downward and the bottom P2A acting upward. If mg is the weight of the fluid in the cylinder, we have P2 minus P1 equal to A mg. P2 is this, because here the pressure will be more and here pressure will be less, equal to mg of this element. Means mg is the weight of this cylindrical element that we have taken for consideration, and these forces are balancing each other out, left and right forces. Only these forces we are taking into consideration, and this equal to P2 minus PA equal to mg. Now if the rho is the density of rho is the mass density of the fluid, we have the mass of fluid is to be m equal to rho v. Rho v equal to v equal to h into a. V equal to a. If suppose a is the pi r square, h a is the that volume of the material. Then P2 minus P1 equal to rho g h. Pressure difference. Let me take fluid under gravity. The effect of this is the diagram that we are taking for this for the consideration. Pressure difference depend on the vertical distance h between point 1 and 2, mass density of the fluid, and acceleration due to gravity g. It is clear from the formula that we derived earlier. If the point 1 under discussion is shifted to the top of the fluid, say the water, which is open to the atmospheric pressure P1, may be replaced by atmospheric pressure PA, and we replace P2 by P. Then equation 10.6 gives P equal to PA. P is the atmospheric pressure and rho GH. Thus, the pressure P at depth below the surface of a liquid open at atmosphere is greater than atmospheric pressure by an amount rho GH. The excess of pressure P minus PA at the depth h is called a gauge pressure at that point. The area of cylinder is not appearing in expression of absolute pressure in equation 10.7. If we see it in 10.7, it doesn't appear anywhere the area. So where does the area disappears? Because here P2 minus P1 equal to area, and when we convert m equal to in terms of density and volume, then we get area on this side also. The both a is cancel out and we will get P2 minus P1 equal to rho GH. The area that means the pressure is not dependent on area. The area of the cylinder is not appearing that we have. Thus the height of the fluid column is important and not the cross-sectional or base area or the shape of the container. The liquid pressure is same at all the points on the same horizontal level at the same depth. The result is appreciated through the example of hydrostatic paradox in figure 10.4. Here this is the hydrostatic paradox. Means if the shape and size are different, The water will take the same level and at the same horizontal position, like here, like here, like here. The pressure will be same, or at the same pressure, means same position, horizontal position, here. Even the shape is changed. It doesn't mean the pressure is different at the same horizontal position. That they are connected at the bottom of horizontal pipe. ABC are connected at the bottom of horizontal pipe on filling with water. The level in the three vessel is the same, though they hold different amount of water. This is so because water at the bottom has the same pressure below each section of the vessel. There is the illustration of hydrostatic paradox. The three vessels A, B, C contain different amount of liquid all up to the same height. What is the pressure on a swimmer 10 meter below the surface lake? So what is the shape of lake? It doesn't matter. It can be this, it can be this, but it doesn't matter what is the shape. Only thing matter is what is the height, and height is given here. So we know the atmospheric pressure 1.01, and then we multiply rho, water density of water, G we know, H is given, then we will get 2.01 into 10 to the power 5 to atmospheric pressure. This is 100% increase in pressure from the surface level at a depth of 1 kilometer. The increase in the pressure is 100 atmospheric pressure. Submarines are designed to withstand such enormous pressure, and we will solve one question: what will be the force at the window of the submarine? Section 10.2.3, atmospheric pressure and gauge pressure. The pressure of the atmosphere at any point is equal to the weight of the column of air of unit cross-sectional area extending from that point to the top of the atmosphere. At sea level it is 1.0013 into 10 to the power 5 Pascal, 1 atm. Italian scientist Evangelista Torricelli 1608 to 1647 devised for the first time a method for measuring atmospheric pressure. A long glass tube closed at one end and filled with mercury is inverted into trough of mercury as shown in figure 10.5a. So first let's go through the figure. Here it is figure 10.5a, the mercury barometer. Here it is the water that we want to measure at which depth we want to measure the pressure. This is a mercury tube, and here there is a mercury vapor. We can consider the pressure here is almost equal to 0. And pressure at B and C are equal because at the same height that we have studied in the last section. Now this device is known as mercury barometer. The space above the mercury column in the tube contains only mercury vapor, whose pressure P is so small that it may be neglected. Thus the pressure at point A equal to 0. The pressure inside the column at point B must be the same as the pressure at point C, which is the atmospheric pressure PA. So PA equal to rho GH, and if we where rho is the density of mercury and H is the height of the mercury column in the tube. In the experiment it is found that mercury column in the barometer has the height of about 76 centimeter at sea level, equivalent to 1 atmosphere, 1 atm. This can also be obtained using the value of rho in the equation 10.8. A common way of stating pressure is in terms of centimeter or mm. If it is 76 centimeter, you can write 760 mm. 760 mm equal to 76 centimeter. You use this conversion. If the question is in centimeter, you do it in that, and if the question is in millimeter, you have to solve in the millimeter. 1 torr equal to 133 Pascal. 1 mm of Hg and torr are used in medicine. The mm of Hg and torr are used for medicine and physiology. In metrology, a common unit is the bar and millibar. An open tube manometer is useful instrument for measuring pressure difference. It consists of U-tube containing a suitable liquid, that is low density liquid, such as oil for the measuring small pressure difference, and high density liquid such as mercury for large pressure difference. So in YouTube, we use oil for low pressure difference and mercury for large pressure difference. On one end of tube is open to atmosphere and another end is connected to the system whose pressure we want to measure. 10.5, this is figure 10.5. One end is open to atmosphere and one where we want to measure the pressure. This is P given here, and at the point A and B the pressure is same, and at the atmospheric pressure we know that. So whatever will be the column of this will balance the pressure at A and B is same because of the same horizontal position, because of hydrostatic paradox. The pressure P at A is equal to pressure at B. What we normally measure is the gauge pressure, which is P minus PA, given by the equation 10.8 and is proportional to manometer height h. Here is the height, and if we know the atmospheric pressure, and if we know the this point, and we can calculate the height and we can calculate the pressure at this point. Just we have to know the density of the oil or mercury we are using depending on the quantity we want to measure. Pressure is same at the same level on both sides of U-tube containing a fluid. For liquid, the density varies very little over wide range of wide range of pressure and temperature, and we can treat it safely as a constant for our present purpose. Gases, on the other hand, exhibit large variation of densities with changes in pressure and temperature. Unlike gases, liquid are therefore largely treated as incompressible. The density of the atmosphere at the sea level is 1.29 kg per meter cube. Assume that it does not change with altitude. Then how high would the atmosphere extend? So by rho gh, we can rho is given gh, and we will get that 8 kilometer. But the density of gas is not the same. That is the explanation given here. In reality, the density of air decreases with height. So does the value of G. The atmospheric cover extends with decreasing pressure over 100 km. We should also note that the sea level atmospheric pressure is not always 60 mm of Hg. A drop of Hg level by 10 mm or more is a sign of approaching a storm. So if the 10 millimeter down in pressure, then it seems that there is a storm approaching. Now at the depth of 1000 meter in an ocean, what is the absolute pressure? What is the gauge pressure? Find the force acting on the windows of the area 20 into 20 centimeter of submarine at this depth, the interior of which is maintained at sea level atmospheric pressure. The density of the sea water is 1.03 into 10 to the power 3. So inside the submarine there is atmospheric pressure. So H is given, rho is given, we can calculate P. P equal to PA atmospheric pressure plus rho GH. Here rho is the density of water. GH is known, so we calculate 104. Gauge pressure, we know that P minus PA. So PA is 1, if 1 atmospheric pressure, then we can subtract 1 and we will get the 103 atmospheric pressure. This is simple. The pressure outside the submarine is P equal to PA plus rho GH. We know that 103 plus the pressure outside the submarine is P equal to PA plus rho GH, and the pressure inside it is PA. Hence the net pressure acting on the window gauge is PG. P gauge is acting on the window because inside there is 1 atmospheric pressure. Since the area of window is A equal to 0.05 meter square, the force acting on it is F equal to gauge pressure into area, and we will get this 4.12 into 10 to the power 5 Newton. And the material of glass and any material that is used to construction for submarine should handle this amount of force, withstand, otherwise the submarine will collapse and we cannot go beyond its limit inside the water. So thank you for this, and in the next lecture we will cover the hydraulic machines and we will move forward. Thank you for watching this lecture.